Today we are going to see how to hack the traditional binary search method, which we traditionally we used to write so many times here. So the most common subtle bug here, people couldn't find it up even in the traditional Java library, other libraries now. What is the bug and how to hack by yourself from scratch? So we are going to understand the fundamental routine. Let me write that routine first here. After that, we are going to see how to hack that routine to find that bug, and then we fix the bug as well. Sure. I got to choose some language to show you the binary search. You pick any language of your choice. I'm picking up Java. Let me take up Java here. Let's create what they call one of the under SRC here, one of the class called binary search. Main method to test this. So we know why we use binary search in a sorted array here. If you want to search for an element quickly here in logarithmic time, we use binary search. In other sessions we have discussed the details of binary search routine, but this session we are targeting about how to hack this binary search. So let me finish up the details here. So public static, it returns index where the element is available. Let me write binary search of array, so an element to search. End of this. What should we do here? Now in binary search we need a boundaries here. Start L equal to 0 here, R equal to here, in dot length -1. We got L and R. The first step we do here is find mid index L plus R by 2. So L plus R by 2 here. End of this. Now we'll check here if the mid element index is equal to X or not. If it is true, we return the mid index. Otherwise, we'll check here if X is smaller than in of mid here. End of this. Now we do what? Since X is smaller, right part we need to prune it. R equal to, so mid -1, mid -1. Else, so X is greater, the only change is L equal to M plus 1. This process is not one-time process, it's an iterative process. So that's where I'm going to use a loop here. So till what point should we continue? So we keep on searching from L to R, L to R, L to R. We're pruning half until even if single element is available, we search. If there are no elements now, we just come out of this method here. That means if L is less than or equal to M, less than or equal to R, will L equal to R, still there is single element, even that element might be an X, so the code will check it out. But even if you don't have a single element, means L crosses R, that shows that end of the search operation here. That's why as long as L less than or equal to R, you continue this one. But once you reach out of the while loop, means we don't have the element in the array here, return some negative index. Let me return -1 here. Let me format. So this is how you normally write a binary search routine for searching an element in a sorted array here. How to test this? Let me create some random array here, integer array. In is equivalent to, first we need size. Let's take command line argument here, integer dot, so percent here, percent of args of 0, end of this, semicolon. Once we get n in a way here, so once we get n, let's create random array here. Or in this case, let me allocate size of n. We fill up this array with sorted data here. I starts from 0, I less than n here. So we take from command line plus I, end of this. We are going to fill it up with sorted data, I equal to I plus 1. That means you are filling up array with 1, 2, 3 and so on till n value here. So once you got what they call the whole sorted data, what to search, maybe I call that as target or X in this case. What element to search? This could be some random element between 1 to n. You can give whatever value you want it up. Maybe initially I'm just giving up what they call n. Since 1 to n values are available, since my aim is to make this binary search take, maybe I'm thinking of worst case, to take maximum time. If I give n last element, first go to mid, cut down, cut down, cut down, last element is n, definitely we are going to get success. That index will be written out. So that's why I took x equal to n. Now let me call this binary search and also display what do you get from binary search. Let me invoke binary search of in comma x. So that's what the print statement. Let me run this code, pass the size, run configurations. Let me give up 10 elements, apply, run. Now we know that we got 1 to 10 elements filled up, and I'm giving up n, which is 10 to search. The last index in 10 elements is 9th index anyway. That's why you could see the result as what they call 9. You can try for other elements as well here. Run configurations, other size 100, apply, run. Again we are going to get 99 here. This is going to be the last element. The index is 99 here. You can try little bigger size as well here. So 1000 element sorted array here. We'll get 999. So it seems to us that the algorithm or code is actually working out. Binary search code is working out. But so how to fix? Now what if element is not there? Let's say I give n equal to -1. Element is not there. Let's see what is the result. You are getting -1. You can give different values now. You are going to get correct result. But what is the most subtle bug available in this binary search code? If you really go through the code, so one of the common issues in a computer arithmetic is going to be this L plus R. Whenever you add two numbers in the regular human arithmetic, when you add numbers here, because numbers, any base system is infinite, we always get some number in our human arithmetic. But in computer arithmetic, always we are limited by the size of the type we are using up. Here L and R are integer size, so they cannot really store up infinite data. Since n plus r is given it up, so if you do not know what are the values of L and R, because there is a limit. When you have a limit, when L and R close to be such big limit, the addition is going to be what? So that's where it's interesting to hack this by passing up large values for L and R. To push the what they call large values for L and R, now I cannot really test with simple values for what they call n anyway here. Let me see what is the limit for integer range, so that I can able to guess what values if I can give to L and R, I can force this what they call L plus R to induce some kind of an issue only. That's why let me check first of all what is the max value an integer type can take in Java language. That's where I'm going to display first. So integer dot max value, which is a constant. Let me see what is the valuation. So you can see here, this is the max value in integer here. If you really look at this value here, what is it? So this is 3 zeros here, that means 6 positions now, 9, almost 2 what they call 2 billion elements now, 2 billion some extra value here. So that means what max value an integer can take it up in Java in other languages when size is going to be 4 bytes is going to be so around approximately 2 billion elements now. So if you want L and R to go very big, let me how to create such a big array so that L will be what they call 0 initially, R is big. Now let me push mid to the mid of it, almost like a 1 billion. So 2 billion plus 1 billion, that's where we are pushing the range to go beyond what can be stored inside integer value. That's why. So the only way to hack that is to induce what they call a very big array here to as part of the input to search. How do I really pass that very big value here? Let me go through the configurations again. Let me try to induce. So 1 billion here, got 1000 now. So 10,000, then lakh here, 1 million, 10 million, 100 million here, 100 million, then finally 1000 million, which is 1 billion size. Let's see. So even you can try 2 billion, we are almost getting close to the max limit, still some elements, but I can force quickly here the algorithm to take very higher values for L and R. So 2 billion, apply, run. So let's see, it's out of memory error. That means Java heap space. Let's increase the heap space here. The configurations, max limit I'm going to increase to xmx here. So hyphen flag, the max heap is going to be, let me give up 10 gig innovation. So let's see, apply, run. Can we really get still out of memory error? So run configurations, let's increase further memory share. Let's mean instead of 10 share, I'm giving 16 gig, apply here, run share. Now you can clearly see here, so Java could allocate a 2 billion integer size. Now this is a range here. Now I'm going to give it a comment to this. Now even x equal to -1, I want a successful search, which I'm giving n. Let's go back to our test case. Let me rerun this. Save this. So let's see, there's a red mark here. So this is x equal to n. Let me rerun this. Let's see. So what are I really going to get it up when I really give up n equal 2 billion share? It is giving up array index out of bounds exception. Clearly, look at the line number, which is 9 share. That means m you are getting up what they call L plus R by 2, which is giving a negative index. That's why the error you could able to see here is going to be this kind of value. So this kind of bug is not visible when you really test for very small values here. But if you want to really hack this kind of code where addition is happening in the computer arithmetic here, this is how you can able to hit it up. You got to find out what is the max limit an integer can take it up, force this L and R to to the very higher values. Now mid automatically when you're trying to sum it up, now it is going to hit beyond the boundaries. But you want to really understand details about what is causing this negative index now. Why are you getting negative index when you add two positive numbers? Here L and R are always positive indices only. How are you getting the negative index? What is causing the problem? If you can find the source of the problem, then you can find fix for this, this problem as well. So let's have a discussion around what they call why L plus R by 2 is causing trouble. Then once you get the complete detail, then we are going to suggest solutions, and we'll see in a practice are the solutions will fix this bug or not. Let's move on to the discussion about why is this negative index is coming when you add two positive integer indices.